In today's session, we are going to see about the stability of a system. The stability of the systems can easily analyzed with the help of the output response C of t. So the main area where we have to concentrate is the transient time Ct of t. So that is actually the natural frequency through which we can determine whether our system is a stable system or marginal. So for a stable system, it can be, you can see that the C of t approaches 0 as the time approaches infinity. For the marginal stable system, the C of t is neither decay or growing and it remains in an oscillation. For instability, the C of t grows without the bound, so that means it keeps on increasing in nature, so our system becomes unstable there. So to analyze this one, let us take the second order generally characteristics. So we know that in the denominator it is s square plus 2 omega epsilon zeta s plus omega n square. If we take the roots, we will get two roots, that is s1 and s2. So if you write that equations in a general format, we can write the equation as s1 comma s2 equal to sigma 1 plus or minus sigma 1 sigma and plus or minus j omega. So here we can clearly say that the depends upon the value of the sigma and the j omega. We can say the system is stable system, unstable system, or marginally stable system. So to expand this thing, we'll draw a chart where sigma in the x-axis and j omega in the y-axis. So this graph is called S-plane, just similar like our x and y plane. So here, since we are here taking the S parameter, we'll name this graph as a S-plane. So in the S-plane, as we have told earlier, the x-axis will be of sigma, whereas in the y-axis it will be of j omega. So for a stable in this one, again we can, the center is a 0 for us, followed by the negative axis will be of -1, -2, -3, -3, whereas in the right hand side will be of 1, 2, 1, 3. So the poles location determines whether the system is a stable system or not. Now let us look into the stable system. In a stable system, all the roots has to lie on the negative axis of sigma. So whenever the root lies on the negative side or the left hand side of the graph, then the system is a stable system. So wherever it may be the poles location, but if it lie on the negative side, the system is a stable system. Here we have seen the two roots, both lie on the negative axis. Let's take x1 as -1 and x2 as -2, but still it lies on the negative side. Now if we look, there is a two more is added, x3 and x4. Now what happens here is, now it has a frequency component available, whereas in the two previous scenarios we don't have the frequency component. That means it is a DC one. Now it is a straight away comes into a stable system, whereas when there is a j omega component is there, then our system response will be of having a small oscillations available there. So we can see the graph looks like there is a overshoot and slowly it tries to come to a settling to a required voltage. So this we have this kind of response we have already seen in the last module. The j omega determines how much frequency will be available for us, or it is also called as a natural frequency. Now in this case everything lies on the left hand side of the graph, so all the poles or this system is a stable system for us. When you go for the marginal stable system, here we have to look that in the marginal stable system it will lie exactly on the j omega axis. It can be a positive j omega and it is a negative j omega, and it is a non-repetitive roots. We have to keep in mind it is a non-repetitive roots. So here we can see x1 and x2, so they are not repetitive in nature, so the values can be of plus or minus j, that means plus or minus j1, so it is a not repetitive. Then the system is marginal stable. If we disturb a system little bit, then it can go to a stable or unstable location. So again I have added a few more poles, that is x3 and 4. Still it is in a marginally stable system. When it comes to the unstable, the roots are repetitive in nature. See, the imaginary roots are repetitive in nature. So in previously the roots are not repetitive, here the roots are repetitive. That means the system becomes unstable for us. So if the system has to be unstable again, it has to be lie on the imaginary axis and it has to be a repetitive roots, or if any of the poles lie on the right hand side of the graph, the system automatically becomes an unstable system. So here we have two poles in the imaginary axis as well as on the right hand side, the system automatically becomes a unstable system. Despite of having many poles on the left hand side, it doesn't matter now, our system is unstable.